channel BaluTechLines. So I think in the last class we have completed Fermi-Dirac distribution function, right? So we have seen what is Fermi-Dirac distribution function, what is its mathematical expression, how it varies with respect to temperature and energy level. And if we have also seen that if two energy levels are equidistant from Fermi energy level, what will be the sum of their distribution functions? And also we have seen what is the formula for electrons and holes in terms of Fermi level, and we have seen the formulas of Nc and we have seen the formulas for Nv, and we have seen where will be the intrinsic semiconductor in case of intrinsic semiconductor, and in case of n-type semiconductor, and in case of p-type semiconductor. And also we have seen that in case of n-type semiconductor, what will be the shift? For suppose intrinsic semiconductor, it will be in the middle of EC and EV. So when it becomes n-type semiconductor, it will shift towards conduction band. So therefore, what is that shift? We also have discussed about the formula for that. And in case of p-type semiconductors, what is the shift which has gone below? Okay, so we have seen all of these concepts. Okay, obviously. So I have already said in the previous class that we are going to do some problems on this one. Okay, so we will solve some problems on Fermi-Dirac distribution function and Fermi levels, and we will wind up this lecture, and we will move on to the next concept, that is excess carrier concentration. This will be the last part of semiconductor physics. Okay, so by that we will finish semiconductor physics and we will move on to diagram theory. Okay, fine. So let's start with today's sessions. Okay, yeah, you can see the first problem on the screen, right? So in an n-type semiconductor, Fermi level lies 0.3 electron volts below conduction band at 300 Kelvin. You can observe the questions clearly. In an n-type semiconductor, okay, an n-type semiconductor is given. The Fermi level lies 0.3 electron volts below conduction band. Okay, so the Fermi level lies 0.3 electron volts below conduction band. What does that mean? So they are saying that. So let us suppose this is the thing. This is the conduction band, and let us suppose this is nothing but valence band. So this will be EC. So somewhere over here, let us assume this is nothing but EF. Okay, since it is an n-type semiconductor, the Fermi level lies nearer to the conduction band. So what they are saying? They are saying that in an n-type semiconductor, the Fermi level lies 0.3 electron volts below conduction band. Okay, so the Fermi level lies 0.3 electron volts below conduction band, right? So this is the difference. Okay, they are saying that this difference is 0.3 electron volt, right? So therefore, automatically EC minus EF is equal to how much? 0.3 electron volt. That is the fundamental information that is given at T equal to 300 Kelvin. Obviously, we can also note that T is equal to 300 Kelvin. Okay. Okay, now we will move on to the further question. So if the temperature is increased to 330 Kelvin, okay, so when the temperature is room temperature, the Fermi level, the difference between the Fermi level and the conduction band is nothing but 0.3 electron volts. Now the temperature is increased to 330 Kelvin. Okay, initially it is 300, now it is increased to 330 Kelvin. Then what will be the approximate position of the Fermi level with respect to conduction band at new temperature? Okay, so simply they are asking you that at T is equal to 330 Kelvin, they are asked you to find EC minus EF simply. So we are asked to find this one. Okay, and we already know that EC minus EF is equal to KT into ln of NC upon ND. Isn't it or not? Now, so what they have given, so EC minus EF at T is equal to 300 Kelvin is nothing but 0.3 electron volt, right? So substitute. So 0.3 is equal to K into what is the temperature? It is nothing but 300 into ln of NC upon ND. Okay, let us say this is equation number 1. Now what they are asking that the temperature has been increased to 330 Kelvin. It means that the remaining parameters are constant. Since temperature is 300 Kelvin, so the remaining parameters will be constant. Why? Because they have mentioned only the temperature is increased. They have not mentioned about the NC or ND, right? So they will be constant. Okay, if they have given any information, then only they will vary. Otherwise, they will be constant. Okay, fine. So the second thing, EC minus EF. This is unknown, right? EC minus EF is equal to K into temperature. What is the temperature? Temperature is nothing but 330 K into ln of NC upon ND. All these values are constants. Okay, simply. So therefore, this will be equation number 2. Okay, so make equation 1 upon equation 2. Equation 1 upon equation 2 implies, so that is nothing but 0.3 upon EC minus EF is equal to, if we divide these both, the KK will get cancelled out with each other, and ln of NC by ND will cancel out with each other. You will be remained with 300 divided by 330, right? So 0 will cancel out with each other. Then EC minus EF will be 0.3 into 33 upon 30. Okay, so simply if you use the gate virtual calculator, you will definitely get the thing. So I will solve for you one thing. So if you see the value, what is the value? 0. Yeah. So 33 divided by 30. So you will get a value into 0.3. The value is 0.33. Okay. So simply therefore the EC minus EF is equal to 0.33. Okay. So here you can observe one more thing. So when the temperature is at 300 Kelvin, the Fermi energy level is here somewhere 0.3. So now if you increase when you increase the temperature, so what is the position of Fermi level? It has been decreased towards the EFI, isn't it? So the actual first EF అనేది సో సెమీ కండక్టర్ టెంపరేచర్ 300 కెల్విన్ ఉన్నప్పుడు ఒక పొజిషన్ లో ఉంటే టెంపరేచర్ పెంచినప్పుడు ఇంకా ఏమైంది అది డిక్రీజ్ అయింది. సో కాబట్టి ఇక్కడ మనం పాయింట్ తెలుసుకోవాల్సింది ఏంటంటే the temperature is increased, the Fermi energy level will shift towards intrinsic Fermi level. Okay, intrinsic Fermi level ఎక్కడ ఉంటుంది? సెంటర్ లో ఉంటుంది. సో యాక్చువల్గా ఇప్పుడు ఈసీ అనేది పైన ఎక్కడో ఉంది. సో ఎప్పుడైతే నువ్వు టెంపరేచర్ ఇంక్రీజ్ చేసావో ఆటోమేటిక్గా అది ఏమవుతుందంటే కొంత డిక్రీజ్ అయింది. సో డెర్ఫర్ అది ఎక్కడికి దగ్గరగా ఉన్నది? ఇంటెన్సివ్ కాన్సంట్రేషన్ కి దగ్గరగా ఉంది. ఓకే, సో దట్ ఈస్ ద థింగ్ దట్ యూ నీడ్ టు అబ్జర్వ్ హియర్. ఓకే, సో దిస్ మైట్ బి ద ఫస్ట్ ప్రాబ్లం. సో వి విల్ మూవ్ ఆన్ టు ద నెక్స్ట్ ప్రాబ్లం. ఓకే, so simply simple problem. So the analysis we have already do it. So I have left our calculation for you. You can easily do it. So coming on to the second problem. Okay, in an n-type semiconductor, the Fermi level is 0.45 electron volts below conduction band. Same question. So again, they have given an n-type semiconductor simply. An n-type semiconductor. So the Fermi level is somewhere over here. Okay, so the difference between these two is that is nothing but EC minus EF is equal to how much? 0.45 electron volts, obviously. Right. So moving on to the next thing. Right. So now the doping concentration is increased by a factor. Now the temperature is not increased. Okay, the temperature is kept constant, but the doping concentration, that is nothing but ND, is increased by a factor 5. Then what will be the new position of the Fermi level with respect to conduction band? Same in that question లాగానే, కాకపోతే ఇందాక వచ్చేసరికి మనం టెంపరేచర్ వేరీ చేసింది, ఇప్పుడు ND ని వేరీ చేస్తున్నాం. ఓకే, సో this is the thing, and we are asked to find if ND is increased 5 times. Okay, so ND2 is equal to 5 into ND1 simply. So automatically they are asking that what is the value of EC minus EF. So they are asking the same thing. Okay, so for the first one, if we write this one, so EC minus EF is nothing but 0.45 is equal to KT into ln of NC upon ND1. Okay, at the first doping concentration level, the value is nothing but 0.45. They have given this one. This is one. So coming on to the second one, so this is unknown. EC minus EF is unknown, is equal to KT into ln of NC upon ND2. ND2 is nothing but what? 5 into ND1, isn't it? 5 into ND1. Okay, 5 into ND1, right? Sorry. So if we make some little changes, EC minus EF is equal to KT into ln of, and if you can see that here, ఇక్కడ దీన్ని కొంచెం మోడిఫై చేస్తే NC upon ND ఒక టర్మ్ into 1/5 ఒక టర్మ్ గా రాసుకోవచ్చు, isn't it or not? Right. So that is equal to KT into, ఇది చూడండి log A into B ఫామ్ లో ఉంది కాబట్టి దాన్ని ఎలా రాసుకోవచ్చు నేను? log A, that is nothing but log A is NC by ND plus log B. Log B is nothing but 1 upon 5. Okay, so if you can see that, that implies KT into ln of NC upon ND plus KT into ln of 1 upon 5. Okay, so we have already know that KT into ln of NC by ND is nothing but 0.45, right? So therefore this value is nothing, which you have already done, right? That has been given. NC by ND1 is nothing but 0.45. Here also we are having here ND1, right? So automatically ND1 and ND1. So KT into ln of NC by ND1 is nothing but how much? 0.45 plus KT. KT is nothing but at room temperature. It is nothing but volt equivalent temperature. That is nothing but 0.0259 into log of 1 upon 5. Okay, if you can see, you can find the value. So 1 divided by 5, you have 0.2. So if you apply natural logarithm for that, you will get something into 0.0259 is equal to, get something. So minus 0.04 the plus, so plus 0.45. You will get 0.408. Okay, so you will get 0.408. So you will get 0.408. So this is nothing but the Fermi level in the second case, EC minus EF2. Okay. Okay, when the doping concentration is in here also you can observe one more thing, right? So when the doping concentration is ND1, so automatically this has been the Fermi level is over here, 0. Some 45 or something. So when we increase the doping concentration, automatically it has the distance is being reduced. Okay, initially it was 0.45, now it has become 0.4. So automatically it will be somewhere over here. So therefore, if we increase the temperature, the Fermi level will move towards downward direction. When you increase the doping concentration, the Fermi level will move towards the upward direction. Okay, so these are the two things that you need to infer. Okay, so very simple. So if you know the concept, then you can easily solve the problems. Okay, so as simple as such. So you can see this one 0.45 is equal KT into ln of NC upon ND. So ND is nothing but 5 ND simply. So if you substitute this, you will get this one 0.45 and you can find the value easily, right? Right. So we'll move on to the next one. Yeah. You can see this question, right? You just pause the video and then you note the question and simply you solve. If you cannot solve, if you're not able to solve this problem, then watch the solution. Okay. Find an intrinsic semiconductor with intrinsic concentration is 1.5 into 10 power 10 and rho is equal to 2 into 10 power 5 ohm meter is converted to N type by adding impurities in the ratio of 2 atoms per 10 power 8. జాగ్రత్త చూడండి ఇక్కడ ఒక ఇంట్రిన్సిక్ సెమీ కండక్టర్ ఉందంట అండ్ దానికి ఇంట్రిన్సిక్ కాన్సంట్రేషన్ అండ్ దానికి కండక్టివిటీ ఇచ్చారు. అది ఎన్ టైప్ సెమీ కండక్టర్ లో మారిందంట. ఎలా మారుతుంది? గ్రూప్ ఆఫ్ ఎలిమెంట్స్ యాడ్ చేస్తే మారుతుంది. అయితే ఎలా యాడ్ చేస్తున్నారు? ఎలా పడితే అలా యాడ్ చేయడానికి లేదు కదా. వి హావ్ సమ్ డోపింగ్ స్టాండర్డ్ డోపింగ్ కాన్సంట్రేషన్స్. సో దే ఆర్ సేయింగ్ దట్ బై యాడింగ్ ది ఇంప్యూరిటీ ఇన్ ద రేషియో ఆఫ్ 2 atoms per 10 power 8 atoms. అంటే 10 power 8 atoms కి 2 atoms మాత్రం యాడ్ చేస్తాం. అంతే కదా, మనం ఎట్లా పడితే అట్లా యాడ్ చేయడానికి లేదని చెప్పుకున్నాం కదా ఆల్రెడీ, రైట్? So intrinsic semiconductor is converted into n-type semiconductor with this doping concentration. So operating temperature is at room temperature obviously and VT is 26 millivolts. What is the shift in Fermi level with respect to intrinsic Fermi level? This is very, very important. They are asking that what is the shift in Fermi level in terms of actually, so when we consider this one, this will be EC and let us suppose this is nothing but EV, let us say. So the intrinsic Fermi level will be this one in the middle, EFI. Okay, so this thing will be here, the Fermi level in case of n-type semiconductor. What they are asking, initially it is an intrinsic semiconductor, that means the Fermi level is at EFI. So if you dope some impurities, that is in the ratio of 2 is to 10 power 8, then the Fermi level definitely shift towards conduction band, obviously. So they are asking that what is the shift in Fermi level with respect to intrinsic Fermi level. So they are asking that EF minus EFI, they are asking this one. Okay, so EF minus EFI is nothing but KT into ln of ND upon NA. KT is nothing but what? VT. VT is nothing but how much? 0.0259. That is 0.03 simply. So ND is nothing but donor concentration. So that has to be known. And Na is intrinsic concentration, that is given 1.5 into 10 power 10. So we need to find ND. For ND we have that formula. I have sent you one formula. ND is nothing but impurity ratio. ND is equal to impurity ratio into density of atoms. I have already said you that. Density of atoms. అంతే కదా. మా ఇంప్యూరిటీ రేషియో అంటే మీనింగ్ ఏంటి? మనం ఇచ్చినటువంటి క్రిస్టల్ లో ఒక యాటమ్ కి అంత యాడ్ చేస్తున్నాము అని మీనింగ్, రైట్? సో ఆ వాల్యూ తెలిస్తే దాని టోటల్ నెంబర్ ఆఫ్ ఆటమ్స్ తో మల్టిప్లై చేసాం అనుకోండి, ఆటోమేటిక్ గా నీకు టోటల్ నెంబర్ ఆఫ్ కాన్సంట్రేషన్ వస్తుంది కదా. సో దట్ ఈస్ వాట్ వి హావ్ డన్ హియర్. So impurity ratio into the total number of atoms, that is density of atoms per centimeter cube, right? So if you can see that impurity ratio, they have set that 2 per 10 power 8. This is the impurity ratio, and you have also given the density. Okay, so 5 into 10 power 22. So 5 into 10 power 22. So if you cancel this one, you will have 2 and 6. It will be 10 power 14. 5 to 10, 10 power 14 into 10 is nothing but 10 power 15. This is the donor concentration. So coming on to the problem, so the shift in Fermi level with respect to intrinsic Fermi level is equal to KT is nothing but 0.0259 into ln of ND. ND is nothing but what? 10 power 15 upon Ni. What is the value of Ni? Ni is nothing but 1.5 into 10 power 10 simply, right? So here if you cancel this one, you will get the value of 10 power 5. So if you find the value 10 power 5 by 1.5, so 1 2 3 4 5 divided by 1.5, you will get something. So if you apply natural logarithm, you will have something into 0.0259, 0.0259. Automatically the value is 0.287. So therefore EF minus EFI is equal to 0.2876 electron volts. Okay, this is the thing, right? So simply they are asking you, in initial it is an intrinsic semiconductor, so the Fermi level will be in the middle. So when you do some electrons, so in the ratio 2 by 10 power 8, so automatically it will shift towards conduction band. They are asking you that what is that shift. So the formula we already know, KT into ln of ND upon NA. So for ND impurity ratio into density of atoms, if you substitute all of those things, you will definitely get the value. Okay, so we'll move on to the next problem. Yeah, you can see this one. You can easily solve it. Yeah, you have been asked for this question. So a silicon is doped with boron. Okay, so a silicon is doped with boron. That means it will be because silicon is a pure intrinsic semiconductor. If it is doped with boron, it will become an N-type semiconductor, P-type semiconductor, right? So because it is a group 3 element. To the concentration of this is nothing but acceptor concentration. Why? Since it is a group 3 element. Okay, so 4 into 10 power 17, right? So acceptor concentration Na is equal to 4 into 10 power 17 per centimeter. This is already given. Now, assume Na is equal to 1.5 and 10 power 10 to be to 25 millivolts at 300 Kelvin. Okay, so that is nothing but we already know. Okay, so this is thermal voltage, right? So the Fermi level of the doped silicon will be, okay, so ఎక్కడ మూవ్ అవుతుంది ఇక్కడ జాగ్రత్తగా అబ్జర్వ్ చేయండి అమ్మా ఇక్కడ మూవ్ అప్ మూవ్ డౌన్ అడుగుతున్నారు ఏంటి దాని మీనింగ్ ఏంటి సో ఇనిషియల్ గా ఒక ఇంట్రిన్సిక్ సెమీకండక్టర్ దట్ ఇస్ సిలికాన్ ఉంది దిస్ ఈజ్ ఈవి అండ్ దిస్ ఈజ్ ఈవి ఈసీ అండ్ ఈవి సో ఇనిషియల్లీ సిన్స్ ఇట్ ఇస్ an intrinsic semiconductor the Fermi level is in the middle. Okay, when we dope with acceptor impurities, automatically the Fermi level will shift towards valence band. So right, so ఇది move down, definitely the down move అవుతుంది, right? So అది మనకు ఆల్రెడీ తెలిసిందే, this will be EFI and this is EF. అయితే వాళ్ళు ఏమడుగుతున్నారు ఇంట్రిన్సిక్ ఫర్మి లెవెల్ నుంచి వాళ్ళ ఇంట్రిన్సిక్ ఫర్మి లెవెల్ మెన్షన్ చేయలేదు కానీ అది మనకు తెలుసు కదా ఎందుకని ఇనిషియల్ గా ఇంట్రిన్సిక్ సెమీ కండక్టర్ లో ఉన్నప్పుడు అక్కడ ఉండే ఫర్మి లెవెల్ ఇంట్రిన్సిక్ ఫర్మి లెవెల్ అంటాం. సో ఎప్పుడైతే మనం పీ టైప్ గా మార్చామో ఎంత షిఫ్ట్ అయింది అన్నారు ఎక్కడి నుంచి షిఫ్ట్ అవుతుంది ఫర్మి ఎనర్జీ లెవెల్ నుంచి డౌన్ షిఫ్ట్ అవుతుంది అది ఎంత షిఫ్ట్ అవుతుందని అడుగుతున్నారు సింప్లీ. సో వి ఆల్రెడీ నో దట్ EFI ఇక్కడ ఫస్ట్ పైన EFI ఉంటుంది కాబట్టి EFI మైనస్ EF is equal to KT into ln of Na upon Na simply. Okay, so we already know that KT is nothing but what? So 0.0259 into ln of Na. What is nothing but value of Na? It is nothing but 4 into 10 power 17. And what is Na? 1.5 into 10 power 10. Okay, so here you will have only 7. So automatically if you solve this one, 4 divided by 1.5 is equal to something into 10 power 7. 1, 2, 3, 4, 5, 6, 7. You will have something, and if you apply natural logarithm 17.098. Okay, so this is multiplied with 0.0259, you will get 0.442. Okay, so therefore EFI minus EF is equal to 0.442. Okay, this is the shift in Fermi level in case of p-type semiconductor with respect to intrinsic Fermi level. Okay, so very simple. So if you understand the concept what's happening inside the semiconductor, then definitely you can solve any problem that is given in gate exam. Okay, so first of all you need to understand the concept. Okay, so after that it will be very simple. Okay, fine. So the answer will be something move down by 0.427, right? Yeah, you can see this one 0.427. Yes, right. So these are some of the problems so which has been appeared in previous gate examinations in regarding with Fermi level. Okay, so practice it and practice more and more bits from your materials and all that. And if you have any doubt, place in the comment box. Definitely I will help you out. And those people who are preparing for GATE 2022 and 23, so definitely share our content to them, our link to them. So definitely it will be helpful. And don't forget to like, subscribe, and share our channel. Okay, fine. So we will meet in the next lecture with the last part of semiconductor physics. Okay, so until then, take care and bye.